We've been using this equation, and if we were given the electric field in a region of space, we could find the change in potential. But it stands to reason that we could take the derivative of this equation and use that to find the electric field if we were given the potential. So if we're given the potential in the region of space as some function, we can take partial derivatives to figure out what the components of the electric field are in that region of space. The x component of the electric field is the partial derivative of the potential function with respect to x, and the same is true for the y and z components. That can be written in vector notation like this. The electric field is equal to negative del V. Del is a vector operator, and it's the partial derivative with respect to x in the x direction, the partial derivative with respect to y in the y direction, and the partial derivative with respect to z in the z direction. Maybe an example would be helpful now. Here's a graph of electric potential versus position in some region of space. And we're going to look at various locations. Let's take a look first at location A. If we were located at location A, would we measure an electric field at that location? If so, what direction does it point? Yes, there is an electric field because there's a slope to the electric potential curve. The electric field is negative the slope of the potential curve, negative dV dx. Because our slope is negative, the electric field would point in the positive direction, negative dV dx. So the electric field points in the positive direction if we were located at point A. If I released a positive particle at point A, would it start to move? If so, in what direction would it move? A positive particle released at point A would feel a force because it's sitting in an electric field pointing in the positive x direction, and it would start to move in the positive x direction. Let's take a look at points B and C. How do they compare to point A? Is there anything different about point C because it's below the x-axis? No. All we care about to find the electric field is the derivative of the potential function. That's the slope of the potential function. It's the same at points A, B, and C. So the electric field is the same at all of those places. There's a constant electric field. What happens at point D? What direction does the electric field point there? At point D, there is no electric field. dV dx is 0. The slope is 0 at that point. There is no electric field in that region of space. And at points E and F, what can we say about the electric field there? Is there anything different about point F because it happens to be the point where the potential is equal to 0? No. The slope of that curve is the same everywhere, and the electric field is the same everywhere, and it points in the negative x direction. Now, think about what kind of a charge distribution would create this potential curve. Pause the video and see if you can come up with a charge configuration that would produce this V versus X graph. Let's take a closer look at the electric field in each of these regions. Let's call this region 1, and this will be region 2, and this will be region 3. We know the electric field in region 2 is 0, right? In region 1, the electric field is constant, and it points in the positive x direction because the slope here is negative. Points in the positive direction. And in region 3, we have a constant electric field that points in the negative x direction. And we also know one more thing. We know that the magnitude of E3 is greater than the magnitude of E1 because the slope is steeper there. So see if you can come up with a charge distribution that creates those electric fields. I'm going to start with region 2. I know my electric field has to be 0. So if I put a conductor there, I know the electric field has to be 0. This could be a solid rectangular block that's a conductor. An infinite plate. I know that on the right side, I have to have some negative charge. And on the right side, I have to have some negative charge, but less. What would cause charge to split unequally on a conductor between the two sides? Well, another charge somewhere else, another infinite sheet of charge somewhere else. So maybe I have an infinite sheet of charge over here at the origin. Of course, my infinite sheet would have to have positive charge on it. That would create, in region 1, an electric field that's uniform and points in the positive x direction. And on the other side, I could have another infinite sheet of charge that was positively charged but had a greater positive charge per square meter. And that would create an electric field in this region of space that was a little stronger than the other one, but it was still uniform and it points in the negative x direction. That's one example of a charge distribution that would create this electric potential. You probably don't even need the infinite sheet of charge on the left-hand side. Once you have the sheet of charge on the right-hand side, drawing some excess electrons over to that side, you would get this electric field even without the sheet on the left side. Or there might be another configuration that produces this electric potential. But this is certainly one configuration that would do it. One of the assumptions we've made since day 1 in this class is that when we take two conductive objects and touch them together, the charge splits equally between the two charges, like I've shown here. If I have two conductive spheres, a +6 charge and a -2, and I bring them together and touch them, they become one large conductor. The total charge that's available, +6 -2, is +4 coulombs. And that's going to split equally because these two spheres are identical size. And then we separate them, we end up with +2 coulombs and +2 coulombs of charge. But that's not true if the spheres are different size. And now that we know about electric potential, we can figure out how the charge splits between conductors that have different radii. Let's take a look at this example. I have 3 charged spherical conductors. One of them has a radius of r, the next one has a radius of 2r, and the third one has a radius of 3r. And they carry different amounts of charge. The smallest one has a total charge of -q, the medium-sized one is +7q, and the large one is +3q. If I touch these all together and then separate them, how much charge is on each conductor? When these 3 conductors are touching together, like I'm showing them here, they become one large conductive surface. And what do we know about the electric potential on the surface of a conductor? It has to be the same everywhere. if our conductor is in electrostatic equilibrium, the electric field has to be perpendicular to the conductor everywhere. We cannot have a component of our electric field along the surface of a conductor if it's in electrostatic equilibrium, because charges aren't moving. That means that this whole surface is an equipotential surface. All three of these conductive spheres have to be at the same potential if they're all touched together, forming one large conductive surface. That means that the potential of the smallest sphere has to equal the potential of the medium sphere, has to equal the potential of the largest sphere. What is the potential on the surface of a conductive sphere? Remember, if we're outside of this spherical charge distribution, this conductor with charge on it is a spherically symmetric charge distribution, and if we're outside of that charge distribution, the electric field looks like a point charge at the origin. Well, the electric potential also looks like it's being caused by a point charge at the origin. So the electric potential due to a spherical conductor with charge on it is equal to KQ over R. The potential of the smallest sphere will be KQ on the smallest sphere over the radius of the smallest sphere. That's the potential on the surface of the smallest sphere. That has to equal the potential on the surface of the medium-sized sphere, KQ2R over its radius. And that has to equal the potential of the largest sphere on its surface, because they're all touching together now. We need another equation. We know that the total charge is going to be split between the three spheres. The charge on the smallest, the charge on the medium, and the charge on the largest one. And that has to equal whatever total charge we started with. And we started with minus Q on the smallest one, plus 7Q and plus 3Q. Now I do a bunch of algebra, plugging in, substituting, solving for QR, plugging in, do a bunch of algebra. I'm not going to do it all for you. I trust you can do that. And work through, and what I end up with is QR, that's the charge on the smallest sphere, the sphere that only has a radius of 1r, is equal to 3 halves Q. The medium sphere has a charge twice as much as the smaller sphere, or 3Q. And the largest conductive sphere has a charge of 9 halves Q, 3 times the smallest one. So as the radius gets bigger and bigger and bigger, the conductor has more charge on it, but the charge per unit area is less on the largest sphere, and it's greatest on the smallest sphere. And we talked about that earlier. One of the properties of conductors in electrostatic equilibrium is that the charge density is highest where the radius of curvature is smallest. And that's what we're showing here. If we had an odd-shaped conductor like this, the smallest radius of curvature would have the greatest charge density. And out here, where the radius of curvature is large, the charge density would be much less. So electric field lines become concentrated where you have tight radiuses on your conductors, or points. That's why a lightning rod comes to a point, and the electric field is very concentrated right there. And a lightning rod, the job of a lightning rod is actually to prevent a lightning strike. The electric field is so strong that charges that are building up that are going to cause this lightning strike can dissipate into the air and actually help prevent a lightning strike. That's the first job of a lightning rod. The second job is, if it can't prevent it, you want the lightning to hit the rod. That rod is connected to ground, to earth, and it prevents the building from being damaged. And why does the lightning hit the rod instead of the building? Because of that point it comes to has a very concentrated electric field, and that's where the lightning is attracted. So the point here, we talked about this earlier. You didn't know why the charge density was greatest where the radius of curvature was smallest. We just introduced that fact. Now you know why. Because a conductor is an equipotential surface if it's in electrostatic equilibrium. And that means that every part of it has to have the same potential. So the charge doesn't have to be equal in different places. It has to orient itself, spread out in such a way that the potential is the same everywhere on that surface.